Hi, this is Jason Baker, and welcome to our continuing lecture on containerization and Docker. So, what is Docker? Docker is an open source Linux-based container implementation that was started by a guy named Solomon Hykes, based out of France. And it was originally released back in 2013. Funny enough, it was actually started as part of a different project. Basically, Hykes was trying to build a company that was going to be providing a platform as a service offering. And what they soon found was that this Docker technology they built was actually much more popular than the platform as a service. And so they kind of pivoted the company to focus on Docker instead. And Docker containerization technology is widely used in the marketplace by different cloud providers and many different enterprises. Now, Docker Docker shouldn't be confused with the sort of underlying containerization technology. The way to think of Docker is it's sort of like an API layer that lives above existing Linux facilities like C groups and namespaces. So the containerization technology is actually built into the Linux kernel, and it has been for many years. But the problem was that it was difficult to use. And so Docker came along and they basically built this API management layer and set of tools around the existing Linux containerization technology. And it's that tool set which you can use then to easily make use of containers on Linux. Docker wasn't the first company to do this, by the way. It wasn't the first company to build Linux-based container solutions. In fact, I used Linux containers, many years ago, over 10 years ago. I was using containers on a platform called Virtuoso. And Google has been working with containers for at least a decade, and there have been a number of other containerization technologies available. They just were not really in widespread use, or they were only being used in specific sort of niche markets. So when we're thinking about deploying applications in containers, that application deployment process looks different than a traditional application deployment. With our traditional applications, we're typically shipping packages in some sort of package format. Could be an RPM file or could be a Java jar file. With a container, we are basically shipping the container, and the container will contain our application code and all of the dependencies in that code. With our traditional applications, we've got to deal with different dependency conflicts. With containers, we're not so worried about that because each container it's sort of like its own separate environment with its own set of software dependencies. And containers can work on any machine, right? If they work on your laptop, then they will work on the staging and production environments exactly the same way. So how does Docker work? Docker, as I mentioned, is this API layer, and it really consists of a few different components. It's really a client server system. So there's a Docker daemon, which is the engine, and that daemon runs on a host. It is what allows you to build, run, and manage containers on a server. And then there's also the Docker CLI, and that's a command line tool that you are interacting with. So when you're issuing Docker commands, you are running those commands using the client. The client is then communicating with the Docker engine to actually like instantiate containers. And then the third component is a registry. There's an image registry, a kind of a repository, and and you can store Docker container images in the repository. That might be something that you run locally, or it might be something hosted by a third party. For example, Docker has a registry service that they offer called the Docker Hub. Here's another sort of schematic diagram showing the process and how the client interacts with the daemon. In this case, on the Docker client, you can run different Docker commands. When you run those commands, the client application is communicating with the Docker daemon, and that daemon is then using Docker images to create Docker containers, and it can start, stop, and remove containers. Those images might be stored locally on the system. If they're not on the system, then they will need to be pulled from some sort of external repository. The Docker client and the Docker host could be one and the same. So like the 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 small environment that we use in the hands-on segment of this lecture spins up a single EC2 instance, and that EC2 instance is running the Docker engine, but it also has the Docker client installed, so you can use the client right on the server itself. Okay, there's a few Docker terms that you need to understand before we start jumping into using the different Docker tools. There's the Docker host, and the Docker host is the machine which is running the Docker containers. Each container is built from an image, and an image is a read-only template file, and that contains all the files and metadata that's required to create a container. You can think of a Docker image as being sort of like an AMI, or a sort of a virtual machine image in a sense. It's not quite the same, of course, because containers are not virtual machines, but there are some similarities because it is a template. It contains all of your application code and data and so on. A container then is that super process. It's an isolated application environment that contains everything that's needed to run a particular application. A registry is a service, it's a location where we store a set of images, and we'll use these images then to create new containers. A volume represents a persistent data storage that's located outside of the container. And I'll be talking a little bit more about volumes later in this lecture. And then finally, there's this concept of a Docker file. And a Docker file represents a script, a set of code that we can use to actually build Docker images. Okay, well, let's start jumping in and using the Docker client and running some Docker commands. And I mentioned earlier in the lecture that there is a single node Docker environment that you can launch as a cloud formation stack. And I've already gone ahead and done that. And I've logged into that stack over here. Let me increase the size of this window so maybe you can see it a little easier. One thing to note is that this stack is running Ubuntu Linux, so you will need to log into the EC2 instance using the Ubuntu username. And now that I'm logged in, if I do a docker dash version, then it will respond back with the version for this particular Docker build. At the time this lecture is recorded, the Docker version is 18.03. Okay, so now we confirm that the client is installed. Let's start running some Docker commands. And the first command we're going to run is a very simple command, which will create a new Docker container. I'm going to run this command docker run busybox echo hello world. This is sort of the hello world version of Docker containers. So we run this command and we see a bunch of output, and at the very end we see that it outputted hello world. Well, what the heck is going on here? So what happened is that when I ran this command, Docker created a small container on my server, and it created that container using an image called the busybox image. So this, when I said docker run busybox, I'm saying that I want Docker to run the busybox image. And the busybox image is a very small image that has a small Linux distribution on it that's designed for embedded systems. So these are systems with very small, limited processors. And when it ran this container, it Docker told the container to run a command, which in this case is just a shell command, which is echo hello world. Now, echo hello world, as you know, just simply outputs the text echo hello world. So Docker created this container called the busybox using the busybox image, and within that container, it ran this command echo hello world. And this container is no longer running. So this container was launched, instantiated, and it lived long enough to run this single command, but after it was done running this command, then that container stopped. It no longer exists. So what is all this stuff about, like pulling from library, busybox, pull complete, digest, etc.? Well, when we told Docker that we wanted to run the busybox, when we told it that we wanted to run a container using the busybox image, the first thing that the Docker client did was look to see if the busybox image existed on this Docker host. And because we had never run this container before using this image, the image didn't exist on the local host. So Docker then went out to the Docker Hub registry and pulled down, it downloaded that image. That's what this pulling from library busybox means. It pulled down and downloaded this image, and then it launched a new container based on that image. Let's try something a little different here. Um, we're going to set up and run an interactive container. So when we created this previous container, when we ran the container only lived long enough to actually run our command, the echo hello world command. After it was done running that command, the container stopped. But there might be times where we want to be able to run a container and actually interact with the container. In a sense, we want to be able to log into the container. So let's try this out. We're going to run docker run -it, which means that we want to run the container interactively. We're going to run a container based off of the Ubuntu image. And in the container, we're going to run the bash command, which means that we want to get a login shell or a command shell within the container. Let's see what happens here. Now, the Ubuntu container doesn't exist on the local server, so it needs to go out to the Docker Hub registry and pull down that image. Now it's launched a new container, and you notice that our command line prompt has changed. So this means that we are now actually interactively logged into the container. Any commands I run at this point are running within the container. They're not running on a shell on the actual host. They're running on the container instead. So now that I'm in the container, I can look around. Now this container is running the Ubuntu Linux distribution. So, I would expect to see all the, sorts of, I'd see different parts of the Linux file system. If I do look at the processes that are running in the system, um, you can see that we don't have any running processes. Unlike our host operating system, if you look at the processes running on the host, there's tons of different processes. Within this container, we haven't started up any services yet. So I can, if I wanted to, I could go ahead and install Nginx or install some sort of software package. It's not called Nginx. I'm just going to use, let's see. Oh, I need to install, I'll point it at an actual package repository because it doesn't know where to find these packages yet. But the point is that I could install software packages within this container environment. So I'm going to exit out of here. And when I exit the container, I'm back on my host system. You can tell that because my prompt has changed. Now, so we launched a computer, or we've launched a container interactively. We provided a command and it ran the echo command, and after it was done, the container stopped. And then I interactively logged into the container. So I started up a container. I told it I wanted to run I want to be able to access that container interactively. I wanted to run the bash command so that I get a shell prompt within the container. As soon as I exited out of that container stopped. Well, what if I want to be able to run a container continuously? And I don't want it to run in interactive mode. I just want to start up a container and let it run in the background. Well, I can do that by running a container in detached mode using the detached mode flag. And let's look at an example of how this works. So I'm going to run this container, say docker run -d jpetazo clock. Jpetazo clock is the image that I want to use for my container. And I'll hit enter. Now it's gone out to the registry and downloaded the jpetazo clock image, and it's created a new container. Each container has a digest value associated with it. So that's what this big SHA-256 digest value represents. That's the uh, or excuse me, this is the image that it downloaded, and then this SHA value down here represents the value of the SHA associated with the actual container itself. So now this container is running in the background, and you might be asking, well, you might be saying to yourself, well, I don't see any output from this container. Well, the container is actually outputting some information, but it's being output to the container logs. And we can look at that by doing container logs and then looking at the actual container, which is this SHA value. Now I could copy in this whole SHA value, copy and paste it, or I could just use like the first 4 or 5 characters is usually enough. It's usually distinctive enough for me to reference that particular container. And when I do Docker logs on it, you can see that there's all this sort of this timestamp. So every single second, this service inside the container is creating a timestamp in the container logs. And if I do it again, you'll see that the time keeps incrementing. So this container is running in the background, and it's just got this very simple clock service that is outputting a timestamp to the container log file. And this is just to show you that this container is running. It's running in the background, and it's actually doing something. Well, it's running in the background, but how do I know that it's running? Well, I know it's running because I can get a list of existing running containers by using the docker ps command. And I'm going to expand my display here so it doesn't wrap as much. When I do that docker ps command, it shows me a list of all the running containers. In this case, I just have one. Each container has a container ID, and this shows you the shortened version of that ID. It tells me the image that was used to create the container. It shows me the command, the startup command for that container, how long ago it was created, and how long the container has been up and running. Any ports that are published by the container, and I'll talk about that later in the lecture. And then the container has a name, which is kind of a funny looking name, and I'll explain how these containers are named here in a bit as well. So you can use the docker ps command to look and view the running containers on your system. When containers are running in the background, oftentimes they will output log information. And you saw how I can use the docker logs command to view the logs that are created by services running on a container. And docker logs is a very helpful command because you can use it to troubleshoot what's going on within a container. So our container is currently running. What if I wanted to stop that container? Let's go ahead and do that. So we'll do a docker stop, and then provide our container ID, and Docker will go ahead and stop the container. Now, when Docker stops a container, it tries to gracefully shut down that container, shut down the processes within that container. If you wanted to forcibly stop a container, then you'd use the Docker kill command, and that does not use a graceful shutdown process. That forcibly tries to kill the container process. I try to always use Docker stop if possible and use Docker kill only as a last resort. Now, if I do a Docker PS again, you'll see that there are no running containers. Well, what if I wanted to see a list of containers that were running previously or had been running at some point? I can do that by doing a Docker PS-A. And that will show me a list of all of the containers, even those which are no longer running. You can see here's a list of all the containers that I have created on this server since I launched the server. If I wanted to start up one of these containers again, let's say I wanted to start this clock container again, I can actually start the container. I could do a Docker start and then give it the container ID. Do Docker PS, and there we go. There's my container. It's up and running again. Docker logs, container ID, and the logs or the container continues running from where it left off. You can see there's obviously a gap here in the timestamp because I had stopped that container for a minute or two. I'm going to go ahead and I'll go ahead and stop that container once again. Oops, Docker stop. There we go. Docker stop. Okay. Now, so far when I've been creating these containers, the Docker client has been, providing me with this SHA value associated with the container, this ID value. And that ID value isn't very easy to remember, right? This is the shortened version of it, but it's this like long SHA-256 value. Now, when Docker creates a container, if you don't provide the container with a specific name, then Docker will automatically assign a name for you. And you can see some of the names it has assigned these containers, like Gallant Thompson and Condescending Engel and Happy Easley. These names are a combination of a mood and an inventor, a scientific inventor name. So that's kind of like this funny naming scheme that Docker uses when you launch containers and don't provide those containers with an explicit name. We can, of course, give our containers name, and we can name our containers using the name parameter. So, for example, we're going to run a new container using that clock, and we're going to call it the TikTok container. Now, you can see that this container is outputting that timestamp directly to my standard output. That's because I'm not running this container in detached mode. I'm running it interactively. So it's going to output directly to my terminal. I'm going to cancel that by doing a Control C. And then if I do a Docker ps-a, you'll see that I was just running this clock container, and the name of that container was TikTok, which is the name I provided to it. If I don't like the name for an existing container, I can rename it using the Docker rename command. So I can rename a container from one name to another name. When we're creating containers, we are creating containers based off of an image. And when we run a container, we have to specify the image that we're going to use to create that container. So let's spend a little bit of time talking about images, because this is one of the more complex topics when talking about Docker containers. So a Docker image represents, like, it's essentially a template that contains a copy of files and metadata, everything required to run an application. The image itself is made up of multiple layers. So you have to think of a Docker image as being like a layered cake. The bottommost layer, sort of the foundational layer, is going to be some sort of, of base image. And this base image typically represents a Linux distribution of some sort, right? Because remember, a container does not contain an operating system. A Docker image does not have an operating system installed on it, because it is using the operating system from the host. It's using the kernel from the host. The image, however, will have some sort of like base Linux distribution installed on it. And that Linux distribution could be most any Linux. It could be, Ubuntu or Debian or Red Hat or Alpine. It could be a variety of different Linux distributions. And then on top of that base image, you'll have other layers, and each layer could be a different a software application that's installed on the image. So um, what 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 Docker does when it's creating this template is it allows you to build up an image using these multiple layers. And the advantage is that you can then add, change, and remove different layers of the image without having to change the entire image. So like, if you install a piece of software and that software lives in one layer of the image, if you wanted to remove or change that software, you don't have to change the entire image. All you have to do is change that one specific layer. And when Docker is downloading these images, and when it's pulling them from a registry, it's going to pull all the individual layers of the image. And there might be cases where you have multiple images that are sharing some of the same layers. And what that allows Docker to do is to optimize the amount of storage space that's being consumed on the Docker host and greatly reduce the amount of downloading time and the amount of memory that's required to run containers, because these containers can share one or more layers of these images. Now, when you access a container, or when an application is running in a container, the application doesn't see all these different layers. So from the perspective of a process that's running within the container, it appears as though all the different layers of the container have been flattened. And that's what we call the unified file system. From the perspective of a process running in the container looks like one big unified file system. Imagine all these different layers that have been all smashed and merged together. They've all been unified. These images are read-only file systems. So you use an image to create a container. And so the container, when it starts up, it starts up using this image. As soon as the container begins to write data, then that data is written, think of it as being written on sort of like a new layer. So it's not going to be writing data to the actual image itself. It's going to be writing new data on layers above the image, again, as part of this unified file system. You could use then, if you start thinking about it, because we're writing data on layers above the image, we can then use a container to create a new image eventually, because that new image will just be comprised of the previous layers of some previous image, plus the new layers that have been added by the new container. So I mentioned that it's not possible to modify images. These images are read-only. However, we can, of course, create a new container from an image. So we do that by creating a new container using an image, an existing image. Then we make changes to the container. Those changes will create a new layer within the container. And then we can create a new image by essentially stacking this new data layer on top of the old image. And I'll show you how this works here in a bit. Now, when we're referencing layers in something like a Docker registry, or excuse me, when we're referencing images in a Docker registry, there are three different ways we can namespace an image, or in other words, three different ways that we can reference an image. And you've seen me use two of these different namespaces. When I reference an image in the registry, I can just provide, in some cases, a single name, such as BusyBox. When I said Docker run BusyBox, then what I'm referencing is what's called an official image. And this is an image that is officially maintained by Docker. And there are a whole set of different official images that you can pull down. And most of these are sort of general purpose utility images. In some cases, we'll use an official image as a starting point for building our own image. For example, I might use the Ubuntu image, which is an official image, as a starting point for building a new image. I can also reference images by prefixing them with a Docker registry username. For example, the jpetazzo/clock image. The first part of this image name, the JPatazo part, denotes the fact that this image is maintained by a user, by someone who has a user account in the Docker Hub registry. And then the second part of the name, the clock part, specifies the actual image within that user's account. So I could create a Docker Hub account, which is something I recommend that you do yourself, and I can make images publicly available and allow people all over the world to pull down those images for use in their own application environments. And then the third way I might reference or namespace an image is by specifying a registry name. By default, if I don't specify a registry name, then the Docker client will attempt to use the Docker Hub registry. However, in many cases, like if I'm using Docker within my organization, I will set up a private repository that only my organization can use. And so in that case, when I am referencing images, I would prefix those images with the registry name and a colon. In this case, I'm saying I'm going to access this registry on port 5000, and I'm going to be pulling an image called the WordPress image. Okay, so we've mostly been dealing with containers, and you saw how we could list the containers that are on a machine. You can also list the images. So Docker show images, or I'm sorry, Docker images command, and this will show me all of the images that have been downloaded and installed on this Docker host. You can see we've got BusyBox, Ubuntu, and the JPatazo clock images. Each of one has a tag, which I'll talk about in a bit. Each image has its own SHA value and image ID. It tells me the last time this image was created, and also tells me the size of these images. You can see that there could be a huge difference in the size of these images. That BusyBox image was only a little more than 1 megabyte versus the Ubuntu image was over 100 megabytes. Now, the trend and sort of the best practice when working with Docker images is to try to make them as small and as efficient as possible. And that's because then they take up fewer storage and oftentimes fewer memory resources on a system. So it's very, very common to see Docker images that are tens of megabytes versus hundreds of megabytes. If we want to pull images from the Docker Hub registry, then we can use the Docker pull command. So we haven't explicitly been pulling images because if we run the Docker run command and then provide it an image name, if that image doesn't already exist on the system, then the Docker client will automatically try to pull that image from the Docker registry. But if we wanted to just pull an image directly, then we could do that. So Docker pull Debian Jesse, and it will go and download and pull that image directly from the repository. Docker images, now you can see the Debian image is now installed on my local host. And when it pulls that image, I don't know if you caught that while it was pulling the image, but it was actually downloading each layer of that image individually. Each of the images that you have on your system has a tag associated with the image. Think of a tag as being like the version of the image. Now, if you don't specify which version of an image you want to pull down, then the Docker client will automatically pull the latest version of an image. So you can see it says the latest, the tag for many of these images is the latest tag. Using the latest tag doesn't really tell you which version you're using. All you know that is that you're using the very latest version. And it can be sometimes a little bit problematic to just be pulling the latest version of containers because you might not really know like what's changed in the container. And oftentimes in practice, we'll try to pin the version of a container to a specific version tag. This Debian container that I pulled down is using a tag called Jesse. So Jesse is the code name for that particular version of the Debian Linux distribution. And so I know that I've explicitly I'm using the Jesse version of that Debian container. So let's go ahead and run through a process of actually building a new image. And we're going to build a new image by starting with an existing image. And this is a very common pattern. It's very rare that you would actually try to build an image from scratch. And it's actually kind of a complicated process. So it's almost always the case that you start by taking an existing base image, either an official image provided by Docker or somebody that you trust within the Docker community, and you create a container using that image, make a modification to it, and then you create a new image based upon that modification. Let's go ahead and do that. So we're going to do a Docker run. We're going to interactively run the Ubuntu container, and we want to get a bash shell. So it starts up. Notice that that container started up really fast. Well, that's because we've already downloaded the Ubuntu image. So when we need to create a new container based on that image, we don't need to download it again. We can skip that step so that the new container starts almost instantly. We're logged into the container. Let's go ahead. We're going to install a apt-get update on the container that will pull down all the different package repositories. And now we're going to do an apt-get install. We're going to install an application called Figlet. And okay, so we've installed the Figlet application. And then finally, we're going to exit the container. Now, when I created that container, so here's our container ID. You can also do a docker ps-a. And here is that container that we were just running. We didn't give it a name. I probably should have, but Docker gave it a name for us called Sharp Euler. And the container isn't running anymore, but let's take a look at what was in that container. So if I do a docker diff command on the container, it's going to show me all the things that I've added to that container. So this is showing me the differences between what was installed in that container and what was installed on the base image. And you can see that like most of the changes involve this Figlet application, which was installed. So this is just showing you that at the container level, the container because I've made modifications to a running container, I've now created sort of this new layer of data. And that new layer of data contains all those changes. And the diff command shows me the differences between the underlying base image, which is read-only, and the changes that I've made and a new layer above that image that exists within the container. Well, what I want to do is I want to create a new image which contains this new layer. I don't have to build a whole new image. I just need to build an image which contains the base image from that container and the new image layer that I've created when I use that Figlet command. So let's do a new image. We'll commit that new layer by running the docker commit command. And that effectively creates a new SHA value, which represents a new image ID. So if I do docker images, then you see now there's a new image ID up here. Now that image doesn't have a name. I could give it a name. And you see it's a little bit larger than that Debian base, or excuse me, a little bit larger than that Ubuntu base image that we used. So we're going to use this new image ID and we're going to run a container. So we're going to say docker run interactively. We want to run that new image. Because again, my image doesn't have a name, it just has an ID. So I'm going to run a new container using my new image. And so now I'm in a new container running my new image. And I'm going to try to use the Figlet command. Say Figlet hello. And when I do that, then all the Figlet command does is it takes some text and it outputs it in this sort of ASCII graphical format, which is kind of cool. Now, if I want to tag my container, I could do that. I could say docker tag image ID Figlet. And so now my new image has a name, and it has a name called Figlet. Now, if I wanted to, I could tag it. I could tag that image. I could tag it with an actual like version number as well. So I could do Figlet :1.0. Do Docker images again. And now you see that it looks like there's two images. There's not actually two images. You see they both have the same ID. But I can now reference that image just by saying Figlet latest, or I could say Figlet :1.0. They both reference the exact same image. But tagging your images is a very good idea.